Hi, this is Brett Sanders, and this is the second introductory video on PRIMo modeling. In the first video, I showed how you can download or take a zip file with the PRIMo installation, unpack it, and then you'll see the files located in there. We worked through how to compile PRIMo, and we can do that again here. Just with a G-Fortran command, we can compile PRIMo. In this case, I get a warning message, but the compilation was successful. We then configured the input files for PRIMo, going through this primoprep script. We ran that script. It showed us our model domain, in this case for the Miami-Gate area. And we also walked through setting up a basic PRIMo input file, which has information such as the upscale factor to use, whether to load a land cover file, which then controls the Manning coefficient and a runoff coefficient, and also a line of data to control different types of output, and a line of data which controls how long the model is set to run for, in this case an hour, 3,600 seconds, with output every 360 seconds. And we had very simple inputs for the first run. We just had wall boundary conditions on all sides, and then all the other options were deactivated except for this stability option, which I tend to use all the time. Okay, so as the first next step, what I'd like to show you is how you can change the boundary conditions and then get a different solution. So the boundary condition I'm going to suggest we change is the outlet boundary condition, which we can see when we run this primoprep script. So this site, this Miami-Gate test site, includes a section of the Miami River and another tributary channel coming into that canal. And as of now, we're running a simulation assuming rainfall on this entire area and walls for all of the boundary conditions. So now what we'd like to do is add a water level boundary over here at the outlet, so we could simulate, say, a rising tide or a falling tide or some ocean forcing on this model domain. Okay, so to do that in PRIMo, what we want to do is go down to the boundary options and change this to a 1, which means we're going to give it information from a boundary file. And we're also going to open this file called miamigate.bound. That's going to have information about this boundary. So the formatting of this boundary file, there's first just some text that's read in as a header, and then you tell it how many different boundary conditions you want to specify on this domain. And we're going to be adding just one boundary. And what we're going to do is then fill in a table, where the table has several columns, an index, which just goes 1, 2, 3, is a counter, an option here to either use a constant water level, in which case we don't use a file and we select no, or a time-dependent water level, in which case we specify a 1, and then we give it a file name. We tell it the X location and the Y location of the boundary that we want to, of where the boundary condition is going to be specified. And we also give it a distance tolerance, which tells PRIMo that any cell within this distance of this point falls within the boundary. Next, we have an input, which is the water level that would correspond to a constant forcing. So in the event that use file is set to 0, the model will enforce a constant number given by this H-bound. And then lastly, the table has a file name. So walking through this setup, we have 1, which is the first, the value of the index. Use file is set to 0. That means that PRIMo will specify a constant boundary water level. The X and the Y location of this boundary are set to these numbers, which, if we scroll this downwards and we zoom in here, that point is right here at the outlet. So you can see that the X location is basically minus 80.42243, roughly 3. So that puts us right about here. And then the, I'm sorry, I got that wrong. So yeah, minus 80.2433 puts us right here. And the Y coordinate is 25.7948, which puts us here. And so you can see that the boundary point is specified in the center of the channel. And I give it a tolerance of 2 times 10 to the minus 4, which takes me basically to here or here along the boundary. So you give it a point, you give it a distance tolerance, and then any of the boundary cells that fall within that distance tolerance will be assigned this boundary condition. So the first simulation that we ran, we can animate one more time so you can visualize once again the first simulation. So it's rainfall on top of the ground and water is accumulating over time. This is the coarse grid representation of that same scenario. And now what we're going to do is, starting time 0, we're going to specify at this boundary here a water level of 2. And that's because this number here is set to a 2, and this number here, 0, is set to, which tells Primo to specify this constant value. You can also see the vertical scale here. It's going from 0 to 10. So a value of 2 is going to set us quite a bit higher than the current level here, and it may cause overtopping of the banks. So let's go ahead now, and we will save that file. We will confirm that the input file is now set the options bound to 1. We'll save that file. And since we already compiled Primo, we just need to run it again, which is with this command. So /bin PRIMo-GPU, then the name of the directory, which is Miami Gate. So Primo starts, it reads the input files. From the fine grid data that was specified, it creates this coarse upscale grid, where it does the upscaling, downscaling every time step to advance the solution efficiently and accurately. The initial conditions are set, and then the model runs. This model run just takes a minute or so. So shortly we should be seeing the cursor return showing us that the model's completed. In the meantime, when we're ready to visualize the results, we can just go back to this same PrimoViz script, and it's going to load the latest model runs into it. Okay, so the model's now finished. We've got this cursor back. So now if we replay this Matlab script, which, as a reminder, it's a script that loads all of the output files generated by Primo and creates an animation. And it allows you to animate both the fine resolution solution, which is HD. D stands for downscaled, H stands for H, and then also the values of eta, U, and V, which allow us to create this coarse grid animation. So I'll run this script. Now the water's rushing in from the boundary up the canal, and that's visualized both on this coarse grid and on the fine grid. So you can see how that kind of changed the nature of the dynamics inside the model. One other thing that is always a good idea to do is, after the model runs, to load the log file and double check that the model gave reasonable mass balance. So this log file just has a report that it Primo initialized, did the pre-processing, it started time stepping. It reports the time step number, the magnitude of the time step, and the cumulative time. And as the model moves over time, the time step will change depending on the flow conditions. It'll adjust to maintain a stable and accurate time step. And by the time we get to the very bottom, we hit 3600. Then it gives you a report that the model took 43 seconds to run. A mass balance check. Mass was balanced to 10 to the minus 6. We have sort of initial volume, final volume, negative volume. This is the volume of water added by precipitation. This is the volume of water that infiltrates into the ground. In this simulation, the model uses a runoff coefficient that's linked to the land use. And so the runoff coefficient specifies what fraction of the rainfall turns into runoff, and the remaining fraction is taken as infiltration. So that's just a budgeting of the rainfall into runoff and infiltration. There's also a number here for the volume of water that left boundaries. So it's a net flow out, and in this case, since the water came in, it's showing up as a negative number. So this gives you a distribution of flows through boundaries, initial volumes, final volumes, an accounting of water. And what you're looking for is a model that has a really small residual so that it keeps track of water without losing it numerically. Hope that gives you a sense of how you can manipulate boundaries. One more thing you could do with this boundary file is use a time series of water levels from a file. So in this case, I've got a file that's already set up, and you can find that in the test data that's shared with the zip file. Suppose we want to rerun the model one more time using that as a forcing, so we just change that to a 1. If you want to see what's inside that file, we can open up the time series folder, open up this file, and you can see the way that the data are formatted. You have several different header lines. So a header with the date and information about the station, when the timing of the data begins. So this is data starting at 2021 on November 4th at 00 time. And then you tell it the length of the record, the time interval of data in minutes, and then the remaining time series. So this number here represents how many floating point numbers are in the list. This number here represents the time interval of the data, and then the remaining numbers represent water levels. So this model should begin at a water level of negative 0.347, and then the water levels will drop, and then they'll increase again. If you go in time, you can see we run back through reaching a high tide of like 1.7 meters. So it goes through several tide cycles. This model configuration right now is set up to run just an hour. So you'd only run through, a subset of these water levels if I were to run it at this time. So I won't do that, but hopefully this is clear then. The steps to use a coastal water level would be to create a data file like this one that matches the water level data that you want to specify. Typically we grab this from gauge records that are available online. We go ahead and configure our boundary file with the name of that input file and a 1 here telling PRIMo to use a time series. And this input remains the same. You specify boundary forcing. If we wanted to run this model for a much longer period of time, say 12 hours, then what I would do is I would sort of do a quick calculation. If I want to run this for, say, 36 times 12, I will, say, change this number to 43,200, which is 12 hours. I don't want to have too many output files, so I would change this number to, say, 3,600 seconds, and that would output data every hour. I would save that, and I would let the model then run. So the model's running now. It's going to take a while to finish, so I won't have you wait with me. But that's the idea behind the boundary forcing file.